Hello everyone! In this presentation, I will talk about parallel architectures, the main types of parallel systems, and the Flynn classification, which is a common way to categorize computer architectures based on how instructions and data are processed. Now, what are parallel architectures? Parallel architectures are computer architectures designed to execute multiple computations simultaneously. So instead of solving a problem sequentially using only one processor, the system divides the problem into smaller tasks that can be executed at the same time by multiple processors or cores, as I explained in the previous video. So the main goal is to increase computational performance and reduce execution time. Parallel architectures are widely used in supercomputers, multi-core processors, GPUs, clusters, and cloud computing environments, where large amount of data need to be processed efficiently. Now let's see the main types of parallel architectures. So parallel systems can be organized in different ways depending on how processors access memory and communicate with each other. One important model is the shared memory multiprocessors. In this architecture, multiple processors share the same main memory and communicate by reading and writing data in that shared memory space. So this model simplifies communication between processors, but it can also create bottlenecks if many processors try to access memory at the same time. Another type is the distributed memory multicomputer architecture. In this case, each processor has its own local memory, and processors communicate with each other through a network using message passing. This architecture is highly scalable and it's commonly used in clusters and supercomputers. The third model is the distributed shared memory, which combines characteristics of both approaches. In the system, memory is physically distributed across multiple machines, but the system provides the illusion of a shared memory space, making programming easier while still maintaining the benefits of distributed systems. These architectural models define how processors cooperate, exchange data, and execute parallel programs. Now, let's see another important way to classify computer architectures that is the Flynn classification. This way to classify computer architectures was proposed by Michael Jr. Flynn. So this classification is based on the number of instruction streams and data streams that a computer can process at the same time. So based on this idea, computer architectures are divided into four categories: the SISD, the SIMD, the MISD, and the MIMD. Each category represents a different way that instructions and data are handled in a computer system. Now let's see the SISD, which stands for single instruction, single data. In this architecture, a single processor executes one instruction at a time on a single stream of data. This corresponds, look here. This corresponds to the traditional sequential computer architecture. So here we have no parallelism. An example is the IBM 701, which is this really old machine here, which was developed in the 1950s. So SISD systems are typically used for basic sequential programs and simple data processing tasks. Now the SIMD, which stands for single instruction, multiple data. In this model, one instruction is applied to multiple data elements at the same time. Look at here the model actually. In this model, like we can see here, we have a lot of data and a lot of the processing unit execution with the same instruction. So this architecture is very efficient for problems where the same operation must be repeated across large data sets. A classic example is the iliac for, I don't know if I am pronouncing it right, but I think it's iliac. Um, and the modern GPUs, almost all of them use the SIMD. So applications include image processing, graphics rendering, as the GPUs, scientific simulations, and machine learning. That is a really cool thing, right? So let's see the MISD, that is multiple instruction, single data. In this architecture, multiple processors execute different instructions on the same data stream, like this. This type of architecture is quite rare in practice. It is mostly associated with fault-tolerant systems and safety-critical computing. The fault-tolerant systems is where multiple processors analyze the same data to ensure reliability. So, an example is the Space Shuttle Flight Control Computer, where redundant computers process the same data for safety, in this example. Now the MIMD, that is multiple instruction, multiple data. In this architecture, multiple processors execute different instructions on different data simultaneously. So it is everything execution with everything at the same time. This is the most common architecture used in modern parallel systems. An example is the Cry T3E, which is a massively parallel supercomputer. MIMD architectures are widely used in scientific computing, weather forecasting, large-scale simulations, and high-performance computing. Now, to conclude, parallel architectures allow computers to solve complex problems much faster by using multiple processors working together. Different architecture models define how processors communicate and share memory, while the Flynn classification help us understand how instructions and data are processed in the systems. Because of this, parallel computing plays a key role in solving large scientific and engineering problems. So, thank you for watching. Bye bye.